Hi, my name is William, and today I'll be talking about learning domain-independent heuristics over hypergraphs. So first off, what's unique about our approach for learning heuristics? Well, we're able to learn entirely from scratch. And to give you a few examples of how our approach contrasts with related work, we're not using any handcrafted features for a given domain or any existing heuristics as input features to our model. We're also not trying to learn an improvement upon an existing heuristic. We're trying to learn a completely new heuristic from scratch. Additionally, our models are able to generalize to problems not only from different initial states and goals, but also to problems with different numbers of objects. More powerfully though, we're also able to generalize to problems from different domains, and that includes domains that were not seen during training. And that's sort of a crux of learning a domain-independent heuristic. We'll be considering strips problems, where basically you have your set of propositions and your set of actions, where each action has its preconditions, add effects, and delete effects. The solution to a strips problem is a sequence of applicable actions taking you from the initial state to a goal state. So now, what is a hypergraph and how does it relate to a planning problem? Well, a hypergraph is just an extension of a normal graph, where instead of a normal edge that connects two vertices, we have a hyperedge that connects any number of vertices together. And we can actually represent the delete relaxation of a problem as a hypergraph. So just recall that in the delete relaxation, we're ignoring the delete effects of each action. So in our delete relax problem, each proposition is going to be a vertex in our hypergraph, and each action is going to be a hyperedge connecting the set of preconditions to the set of add effects. So many existing well-known heuristics already use this hypergraph structure. So what we're trying to do is essentially estimate the shortest path from a set of initial propositions to the set of goal propositions. And the way HAD does this is that it estimates the cost of achieving the goals as the sum of the costs of achieving each of the goal propositions. Obviously, this is not admissible as we may overcount. On the other hand, HMax estimates these shortest paths by just taking the maximum of the most expensive proposition. The intuition behind our work is, can we learn a function which better approximates this shortest path from a set of initial propositions to the set of goal propositions? And more formally, what we have is we have the hypergraph induced by the delete relax problem, along with the input features for each proposition and action in our problem. And using that, we want to learn a function that maps this hypergraph to a single real number which represents our heuristic value. So the way we're going to achieve this is through hypergraph networks, which is our generalization of the graph networks framework to hypergraphs. And basically a hypergraph network consists of multiple HGM blocks. An HGM block is a powerful and flexible building block that basically computes hypergraph to hypergraph mappings. And it uses a concept of message passing to aggregate and update features within the hypergraph. So just a brief overview of how it works. Firstly, what we do is we compute a hyperedge update. And that basically computes a new hyperedge feature for each hyperedge in the hypergraph based on what it's connected to. Then we compute a new vertex feature for each vertex in the hypergraph based on what it's connected to as well. And basically, the idea is we're using the connectivity information of the hypergraph to pass messages between the vertices and the hyperedges. After that, we'll compute a single global update using all the vertices and hyperedges in the graph. In our case, this global feature is just going to be the heuristic value. So I'm going to talk about strips HGN, which is our specific instantiation of a hypergraph network. And it basically follows a recurrent encode, process, decode structure. So firstly, we have our input features to the network, along with the hypergraph structure. We pass it to the encoder block, and within the encoder block, what it actually does is that it independently encodes the vertex and hyperedge features. And that's using these edge and node blocks which have these phi functions. And these phi's are basically the update functions within the HGM block. In our case, we'll be using multi-layer perceptrons. So we've encoded our input features into latent space, and let's also assume that we have our recurrent latent features at timestamp t-1. We're going to feed this to the core message passing block, and this is the block that basically propagates information through the hypergraph. So looking inside the block, on the left we have our input features, which is our hyperedge features at timestamp 0 and timestamp t-1, also our vertex features at timestamp 0 and timestamp t-1. We're going to feed those into our edge block. And our update function in our edge block, which is a multi-layer perceptron, is going to compute new hyperedge features. Then we're going to compute new vertex features using the input vertex features, and also the aggregated hyperedge features using these row functions. These rows are basically aggregation functions. and in our case, we're just using summation. So after we've computed our vertex features, we're going to compute a single global feature, and that's going to just represent our latent heuristic value. So now we have our updated latent features, and what we can do is we can feed this back into the core block in the next iteration. So you can see I can feed this back into the core block, and that basically corresponds to passing messages deeper into our hypergraph. And I can repeat this m times, which corresponds to m steps of message passing, and I have my final updated latent features. I can pass this then to my decoder block, and within my decoder block, I'm going to decode my global features, which is basically the latent heuristic value, into a single real number, which represents our heuristic value. So now that we know the architecture of a Strips HGN, how do we actually train it? So we'll be using a very simple set of input features. For each proposition, we basically have a 2D vector indicating whether the proposition is true in the current state and the goal state. For each action, we have a 3D vector indicating the cost of the action and the number of preconditions and add effects. To generate the training data, we're going to run an optimal planner for a set of training problems and use the state value pairs encountered in the optimal plans. So what we're trying to do is essentially we're aiming to learn for optimal heuristic value. We're going to treat the problem of learning a heuristic as a regression problem and train using standard gradient descent methods. So now onto our experimental results. So we're going to evaluate all our heuristics using A-star search. For our baselines, we're comparing against HAD, HMax, for blind heuristic, and landmark cut. We're going to indicate Strips HGN by HGN. We're going to train and evaluate on a single CPU core, and we're going to run the core message passing block 10 times. So that's setting m as equal to 10. So I'm going to talk about some of the more interesting results. For the full suite of experiments, please refer to our paper. So what happens if we evaluate on the same domains that we trained on? So in this experiment, we're going to train on small problems from Xenotravel, Gripper, and Bloxworld, and evaluate on larger problems from Gripper and Bloxworld. So we're training and evaluating a single network on these 3 domains. So looking at these graphs, the x-axis for all our graphs are going to be the problem difficulty, and the Strips HGN is going to be indicated by the red line, where we also depict the 95% confidence interval over 10 repeat experiments. So looking at the number of nodes expanded by A-star for Bloxworld, we can see that we do better than all the baselines, including HAD. So this is indicating that the network has learned some informative knowledge which allows it to generalize very well for Bloxworld. So looking at the deviation from the optimal plan length as well, we deviate far significantly less than HAD. So this indicates that it's quite a promising result. So now onto Gripper. We can also see that our Strips HGN for Gripper does far better than all our baselines. Additionally, we achieve a far better deviation from the optimal plan length in comparison to HAD. Now what happens when we evaluate on domains we did not train our networks on? So within this experiment, we're going to train on small problems from Xenotravel and Gripper, while we're going to evaluate on a new unseen domain, so Bloxworld. So the network has never seen Bloxworld problems before. So looking at the graph on the left, we can see that Strips HGN does better than blind search and HMax in terms of the number of nodes expanded, but we still do worse than HAD and LM-cut. This is not too surprising, given the network may have overfit to problems from Xenotravel and Gripper, but it's still able to learn some form of informative knowledge, which allows it to generalize to Bloxworld, even though it hasn't seen it before. In terms of the deviation from the optimal plan length, we can see that Strips HGN also doesn't do quite badly in comparison to HAD. So in terms of future work, one thing we are looking into is speeding up a Strips HGN. So right now it's a bottleneck as it is quite slow to evaluate. So to improve this, we could optimize our implementation of the Hypergraph Networks framework, or also take advantage of multiple cores, or even use GPUs for parallelization. So right now we're only using a single CPU core for training and evaluation. Another thing we could look into is improving the generalization performance of our networks even further. And this could be achieved by using a richer set of input features, or also a careful study of the hyperparameter space, in a similar vein to Ferber et al. At ECHI, where their work is only able to generalize over different initial states. Thank you for listening to this presentation.